Okay, so welcome to class 30. Where we'll be talking about, let's see if I can move this here because no, was maybe not. Okay, yeah, so that's better. You can have the whole screen. So we'll be talking about interacting gases. Till now, we have been handling ideal gases, and things were easy to calculate the partition function because we essentially had Gaussian integrals sitting in the expression for the, well, we had p squared by 2m sitting in the expression for the Hamiltonian, the potential interaction, potential or the interaction energy, the potential energy was zero. And that made calculation simple because we had to evaluate a set of Gaussian integrals to calculate the partition function and the integral over dq, the position coordinates gave v to the power n. But as soon as you have some weak interaction or weak or strong interaction, whatever, in ferromagnetism, we already had to, which is a very simple model, the Ising model, we had to discuss the mean field theory for interacting systems. Of course, in 2D, it can be solved, the partition function can be solved exactly, but it's difficult, and in 3D till date, the partition function cannot be calculated exactly, right? Uh, even when we were talking about photons, the black body radiation, that was particles were not interacting with itself, so the Z, the partition function, could be broken down into a large number of products. But today we are not going to have any such liberty. And then again, we have to calculate the partition function, because if we calculate the partition function, from that we can calculate other quantities like pressure, volume, and so on and so forth, the virial stress, if you like, and thereby we can obtain equation of state, which is the van der Waals equation of state. We will see on some, I think, in the next class that will reach van der Waals equation of state. So the kind of interactions we are going to consider are short-range simple interactions valid for monoatomic gases, say argon, and we're going to do our calculation statistical physics starting from the microscopics, the interaction potential, in the canonical ensemble, in that the variables are the total number of particles n, the volume of the system v, and your box of gases, argon, let's say simple gas, inert gas, um, is in contact with the heat bath, which is at temperature T. So we're going to consider that the temperature is suitably high and N by V is suitably low, so that we can use classical mechanics, which implies that the interatomic distances are much greater than the de Broglie wavelength, because if de Broglie wavelength, if the interatomic distances are order of de Broglie wavelength, then you have to use quantum mechanics. Having said that, though we are going to basically develop the theory and have some assumptions which are relevant for dilute gases at high temperature, later we'll see, we'll extend the equation of state to even get the van der Waals equation of state, which shows liquid gas coexistence, which means if it's a liquid, it's a dense system, it's an interacting dense systems, right? For ideal gas, you have PV equal to nRT, you are never going to get liquids and gases. But with interaction, with the introduction of interaction, the partition function, and correspondingly, when you calculate the relevant thermodynamic quantities, which in this case is the equation of state, what we'll see that, okay, at high temperatures, we'll have the fluid, but at low temperatures, the system will break up into two regions, depending upon the density, of course. At very high densities, if N by V is very high, then you will have all liquid. If N by V is very low, then you will have the entire box full of a gas. On the other hand, if n by v is that's the density is intermediate, then you could have uh, a, a condition where the box of gas has two separate regions, one of which is full of liquid, it is at high density, and the other part of the system is gas, that's its low density. So you can, even with this interacting systems, I mean, argon does liquefy at sufficiently low temperatures and pressures. So the first thing we have to define, I mean, why are we talking about, am I repeating the word argon? Because this is a simple gas, we can approximate the interaction between the gas molecules as a short range interaction, radially symmetric, and so on and so forth. Because if you were taking more complicated molecules, then you would have to consider the effect of charges and so on and so forth, or dipoles and so on. But here we are really considering relatively inert gases. Yes, there is the nucleus in the center of the atom, and there is an electron cloud around the nucleus. But since it's so inert, basically when two argon gas molecules or any noble gas molecules collide, yes, the electrons cloud repel each other, which means two argon atoms cannot sit on top of each other. There's a mutual avoidance, call it sulfur avoidance, call it excluded volume interactions, call it electronic cloud repulsion. The origin is electron cloud repulsion, so the two particles cannot overlap on each other. And then the interaction between two argon molecules when they are close together is modeled by the so-called Lennard-Jones interaction, where there's an attractive term, sigma. Sigma is, as you shall soon see, is the diameter of a molecule by r to the power 6. And this is an attractive interaction minus sigma by r to the power 6. And the origin of this term is the dipole-dipole fluctuations. And what does that mean? It means that if you have an atom, then since the electrons are moving around the nucleus, there can be instantaneously charge. I mean, it's need not be a spherical cloud, it's spherical on an average, and the center of charge can be displaced from the centers. You could have a locally time varying dipole. And the effect, so on an overall, it is neutral, of course, but then there are local dipoles which are induced, and the dipole moment is changing as a function of time. And when another atom comes, both have fluctuating dipoles. So fluctuating dipoles and fluctuating dipoles, what is the effective interaction? It can be shown, and that's another class that can be shown in something like a soft matter class or some other class, where you basically that the interaction goes as 1 by r to the power 6. So the interaction between two charges goes as 1 by r, the potential, right? And then two dipoles, it goes as 1 by r cube, or the interaction I think goes as 1 by r square, one of those, and I think 1 by r cube, or the force goes as 1 by r cube. Whatever, please look up your Griffith. I think it's 1 by r square. Anyway, so and then a charge and a dipole, it goes further down, and you have two fixed dipoles interacting with each other. And here you have fluctuating dipoles and fluctuating dipoles interacting with each other, and those are called dipole-dipole fluctuations, and that goes as r to the power 6. This has a physical origin, but that atoms are going to repel by a large magnitude when the distance between the two atoms becomes closer then the diameter. I mean, so the center to center distance becomes greater than the diameter, then there will be a strong repulsive interaction, and that is modeled by an ad hoc potential, which is taken to be sigma by r to the power 12. So that's the Lennard-Jones interaction. And this Lennard-Jones interaction is often used for a wide variety of cases. So this is coming really from dipole-dipole fluctuations, whereas this is ad hoc. But it does effectively model the extremely sharply rising repulsive forces when two atoms or two molecules try to overlap. So that's the role of Lennard-Jones potential. So this potential, if it is plotted as a function of r, so if you plot V of r versus r, what you will see that at short distances, this term dominates over this term. Why? Because if r is less than sigma, then you have some number which is greater than 1 to the power 12, and this is to the power 6. So this is much dominant than this term. And as a consequence, you see that the potential rises sharply as you keep on decreasing r. Okay, so there's a very sharp increase, but at a particular value of r, where you can see that if you choose r to be exactly equal to sigma, then these two terms cancel, and that's the point where the potential becomes equal to 0. And what is sigma, by the way? So sigma is essentially, if you take the diameter or the radius of two particles to be sigma by 2. So if diameter is sigma and the radius is sigma by 2, when two particles touch each other, just touching each other, so that's the point where the distance between the centers will be sigma by 2 plus sigma by 2, which is equal to the diameter, right? So when they're just touching, the interaction is considered to be 0, just touching. So that's this point when r equal to sigma. But just beyond r equal to sigma, this attractive part plays a role. And when r sigma by r is less than 1, then this to the power 12 becomes a very small quantity, and it is relatively dominated by this term, and this is a sharply falling term. As r increases, the value of this falls, but it falls more slowly than this term. As a consequence of which, if you do dVdr equal to 0, which is basically to calculate the minima of the potential, if you just put dr equal to 0 and calculate the value of Rc for which the potential is minima, you can easily calculate that the R min, the R for which the potential is minima is 2 to the power 1 by 6 sigma, sigma being the diameter. Moreover, so this Lennard-Jones potentials has two parameters. One is 4 epsilon and the other being the diameter. So the 4 epsilon sets the strength of the interaction, right? So basically, you could the reason you write it as 4 epsilon instead of epsilon is because at the position of the minima at R min, the depth of the potential is epsilon if you write it in this form. On the other hand, in here, if you wrote it as suppose epsilon 1, then the depth of the potential would be epsilon 1 by 4. So it's for convenience and convention. It's a matter of convenience, and hence it has become a convention that the Lennard-Jones potential is written as V of R 4 epsilon in this manner, where, as I said before, that this is added, and this really comes from dipole-dipole fluctuations, and there's a relatively short range potential, because as soon as R becomes greater than 3, the value of the potential becomes very close to 0. Those who are doing the computational physics course, they might come across that you even cut off the potential and set to 0 the value of the potential beyond R equal to 3. Because that saves computational time, but never mind. So this is the end of the potential, which by which we model the interaction between simple monoatomic gases like argon and other noble gases. Now, even for such a potential, times it becomes difficult to calculate the potential of, no, sorry, the partition function. So sometimes it is replaced by a simpler potential where you say that the potential is infinity. So the repulsion between two particles is infinity if the distance between two particles becomes less than the diameter, or call it R0 using the Rife convention. By the way, whatever I'm teaching is from Rife section 10.3 and 10.4, page 418, in case you not noticed. Anyway, so just using the Rife convention, yeah. So if the distance between two particles is greater than R0, where R0 is the same as sigma, then the potential is infinity. Or otherwise, you can choose, and if the distance between two particles, small r, is greater than R0, the diameter, then you say that, well, there is an attractive potential acting, which goes as R0 by R to the power S, and U0 sets the strength of the interaction. And basically, you could set epsilon equal to U0. Right? So that's the strength of the interaction just beyond R equal to capital R0, that R, the small r being the distance between two particles. So that's the strength of the interaction, and it's must be given with a negative sign. And if you choose S equal to 6, which is the most appropriate potential, it would correspond to the R to the power 6 terms of the Lennard-Jones potential, which comes obviously from the dipole-dipole fluctuations. Right, so this is the picture. So these are two particles. The distance between centers is R0. When the distance between particles is less than R0, it has infinite, as it has a sharply decaying attractive potential. And beyond a certain distance, it goes very close to 0 because it's R to the power 6, right? With R sitting in the denominator, R, small r sitting in the denominator. What is the point? The point, if you had to do statistical mechanics, our aim is to calculate the partition function. So this is the expression for Z. Z is 1 upon n factorial. You're considering, well, you're considering that the particles are identical. In that sense, it is quantum mechanical. But otherwise, we're just using the quantum the classical Hamiltonian, 1 upon s to the power 3n, right? And integral over all coordinates, the momentum coordinates, and the position coordinates, x and dimension. So since this index is varying from 1 to n, where n is the total number of particles, so I've written it as d3 p1, d3 pn, and everything in between. I could have as well written it as dp1 to dp 6n, 3n. That was also possible, but that's what we have written. So this d3p vector and d3q vector is actually an integral over 6n dimensions, and this is e to the power minus beta kinetic energy plus potential energy. Okay, now one can separate out the position degrees of freedom and the momentar degree of freedom. So the momentar degree of freedom, d3p1, and this is 1, 2, 3n. That is very easy to calculate. These are just a set of Gaussian integrals, and there are 3n variables. So these, so they can be separated out, and this will become 1 upon n factorial s to the power 3n, the phase space volume to the power 3n, and each of these integrals are going to give you square root of 2 pi m by beta, or 2 pi m kbt, right? And since there are 3n independent integrals, you get to the power 3n into ZU. And ZU is the part which has the potential energy and the integral over the real space degrees of freedom. And the challenge is not to calculate, is to calculate ZU. So that is going to be the focus point because, you know, the partition function, the kinetic energy term will always give the same. It's simple. It's always p squared by 2m, and it is always a Gaussian integral. So that part is trivial. If you can do Gaussian integrals, and what is non-trivial is this calculation of ZU, and that is going to be the focus point for the rest of the lecture. Okay, so we're going to introduce these terms back, and we are going to be worried about how to write down ZU, which is an integral e to the power minus beta summation over V of R. Every pair of particles interacting with each other, it could be 0, but if they're within a certain distance, then they have a certain value. Yeah, it will have a certain microstate, certain probability of being found in that particular microstate, and so on and so forth. And this integral is d3q1 to d3qn. N particles, hence d3 x, y, z coordinates. We're considering in 3D. So the next step, so we have to calculate z of u, and considering every pair of particles is going to be difficult because one could be interacting with 2, which could be interacting also with 3, and so on and so forth. So the first simplification, the first aim is to express ZU in terms of the mean energy of the system. And thereafter, we're going to see whether we can somehow take some mean field approximation and write a simple expression, simplify even this calculation of mean energy. So our next step is to calculate or to express ZU in terms of the mean energy of the system. And the mean energy of the system is, of course, going to depend upon beta, because if it has higher temperature, it can access more higher energy microstates, and so on and so forth, right? So in general, the expression for mean energy with n particles, so here I'm reminding you, this is the mean energy of n particles. That is integral over, this is integral over all the coordinate degrees of freedom. But you also have the momenta, but they're going to cancel. They're going to cancel. So ideally, you should have d3q, d3p. But the challenge is primarily in the position degrees of freedom. So this is the, so here you should have d3p also, because z in general has d3p, or else you could write this in terms of dq, and here it should be zu, because the momentum degrees of freedom are going to, I mean, you can either calculate it and then it will cancel or whatever. Yeah, so this should be actually zu. If this is dq, on the other hand, if you write dp also, then this is the general z. But here you have dq. So basically, it's the energy of the microstate, some configuration of particles. Correspondingly, it has a certain potential energy, which is given by this u, q1, q3, which depends upon q1 to q3n. And the e to the power minus beta by ZU would give the probability of accessing that particular microstate. And this is the energy of the microstate. So for different values of different combinations of Q1, Q2, Q3, different values of coordinates, the interaction energy will be different. That will change both the probability of acceptance, but it will also change this energy of the system. For different coordinates, you will have different values of u, and it will be suitably weighted, WEIGHT weighted by that value of u, e to the minus beta ZU. Right, I'm just reminding you that this is the sum overall pair of particles which are interacting, and even if the interaction is 0, so this is over all pairs of particles, the potential energy. And this expression, the general expression of u bar, can be written as minus del beta of log z. of u. And why is that? Why can that be written? I mean, just to remind you, the E bar can be written as EI into e to the power minus beta EI Z summation over all microstates. And this EI can be brought the numerator by taking a suitable derivative with respect to beta, right? I think there has to be a 1 by beta here also. No, maybe not. You don't need del beta, and then EI will sit here, and this minus 1 by z del beta can be written as minus del beta of ln zu. Right? Now, u bar equal to this. What is our aim? Our aim is to write log z in terms of u bar, the mean energy of the system. To that end, this looks like a differential equation. So we take del beta on this side. So integral from 0 to beta, the final temperature, because that's what we are interested in to calculate. U bar, so we are just integrating over. So un bar, the energy of the entire system, del beta dash, and we integrate here from log zu at beta equal to 0, right, to log the value of log zu at temperature equal to beta. When you do this, so on this side you have 0 to beta, u bar d beta. Here you get minus log z beta, so z of u at beta, plus log of at beta equal to 0. This term e to the power minus 0 ur is what you will get, right? And e to the power 0 is 1. So this is an integral over dq1 to dq3n, and which in turn will give you b to the power n, just as we saw it previously. So this term is essentially ln of b to the power n, which can be written as n ln v. Okay. So here there was a minus sign, and this is the lower limit, which will give a minus sign. Hence, this has become plus, and this minus sign remains ln zu at temperature beta, and this term gives you n ln v. So what you have is ln zu beta will do n ln v, which is this term, minus 0 to beta average energy beta dash d beta dash. So here you have the average energy of n particles, right? And that's a function of beta dash, of course. But here we are going to do a fantastic simplification. And this is step 4. So I'm highlighting all the primary steps that we are doing. So here we define the interaction between two particles. Then we say that, okay, we are going to calculate the partition function, which we broke up into the kinetic energy part and the potential energy part. And then we said, okay, this is our focus. In step 3, what we did is to express Zu in terms of the mean energy of the system, which is a function of beta. And the next thing we are going to do is simplify this mean energy of n particle energy into all possible pairs, n into n minus 1 pairs. And to avoid double counting, you have this half here. N into n minus 1 is practically n squared, especially when n is large. So this becomes half n squared u bar, where this u bar is the energy of interaction between two particles. Of course, if this is going to be a function of beta, this is also a function of beta. Here you have a n subscript to remind you that this is the n particle average energy, whereas this is the average interaction energy between just a pair of particles. Here you are assuming in this that at a time the average energy, I mean, each particle, especially in a liquid, Not in a gas. In a gas, this is a valid assumption. But in a liquid, each particle could be interacting with multiple particles, right? But here, what you are doing is not consider. I mean, you're saying that okay. I mean, we will just consider the pairwise interaction, and if we somehow know the pairwise mean energy of interaction between just a pair of particles, then the energy of n into n minus 1 pairs can be written as half to avoid the overcounting n into n minus 1 into u bar, right? So that's how you get. So it's some sort of a mean field approximation. So the next step to assume is that you have a dilute gas, but when you're going to consider liquid, so we are going to get a equation of state where we're going to extend it to that of a liquid also, liquid phase also. So they're not valid, but it is a very good description. We'll get van der Waals equation of gas, and van der Waals equation of gas is a pretty good description to look at liquid gas phase coexistence and critical temperatures and so on and so forth. So they're assuming a dilute gas in that the motion of each particle is uncorrelated with the position and velocity of other molecules. I've said, well, that is questionable for liquids, but we're going to go ahead with this assumption. Of course, you can also do a molecular dynamics where you have interaction between all particles, but for the analytical purposes, we're going to make some simplifications. And the surprising part is statistical mechanics works really well in spite of these simplifications and regimes where these simplifications might not be valid. That has been tested out. Van der Waals equation is a wonderful it's a very good description of the system. Hence, if we can get van der Waals equation from microscopics, that's great. But to get that, we are making this mean field assumption. Moreover, we are saying it's a dilute gas in that the probability that atom J, so this is the aim is to calculate this U bar. And for that, we are saying that the probability that atom J is at a distance Rj minus Rk. And so basically the distance between a pair of molecules. So this is the position of the jth molecule. This is the position of the kth molecule. And, you know, this is essentially a vector pointing from K to J, right? That was also discussed in the previous class. In case you've forgotten, you just draw. And that is the R vector. And we are assuming that the probability that atom J is at a distance R from the kth particle depends only upon the pair of particles, the potential, the pairwise interaction between this J and kth particle. So we are ignoring three particle interaction. So if because if a particle J is has K and some other particle, then J would be interacting with both, and even K will be interacting with the third particle. That will minimize, further increase the potential, decrease the potential energy, more negative. But we're going to ignore that. We're going to say that the probability depends only upon e to the power minus beta UR, pairwise interaction. So in writing this, we are assuming that it depends only upon the pairwise potential between J and K due D3R. So I have two body potential without any correlation. So the two particle average energy of interaction, average energy of interaction can then be written as U into e to the power minus beta interaction potential between the two particles D3R by Z2, where Z2 is, integral over, so this R vector, this small r should not be there. You should have just integral D3R where r is the distance between two particles. And so here you are saying, okay, these two particles can occupy the entire phase space, and well, ur might be 0. They're very far away, or it might be very low. But it's so basically Z2 is the two particle partition function e to the minus beta ur, where r can take any value, including overlap. But then there the potential will be infinity. So e to the minus infinity will be 0. So that it will have no contribution to Z2. So it's just whatever potential you have, which is the Lennard-Jones potential or the modified Lennard-Jones potential, that you put in here, and that will give you the two particle pair partition function. The average energy is the probability that the two particles are distance r away, which is given by e to the minus beta ur, the potential d3r by z2, and whatever is the energy when the two particles are at a distance r. And this in turn can be written as minus del del beta log of z, the two particle partition function d3r e to the minus beta r, reminding you that this small r is earnest, so z2 is this capital R. So basically, you are just considering what is the average interaction in a heat path of all other particles, and the probability that these two particles will be a certain different distance away is e to the minus beta ur by z2. And you're integrating overall space that is available, right? So that's what we have done. And the step 6 of the calculation is, now this can be very easy, relatively easily calculated. But even then, we are going to basically add a +1 and subtract a -1 from it. And this term will give something called the virial coefficient, but we'll soon come to it. So basically now what we're going to do is integrate over all phase space d3r, right? The distance between two particles, that's this capital R. And if you integrate that over all possible volumes, this will give the total volume of the system. And this part, e to the minus beta ur, two particle potential -1, can be written as I. And we're going to calculate I next. So we're going to calculate this term next, and it will lead to some simplification. So that's why we are doing this algebraic manipulations. Now from this, if we take out V, you can write it as 1 plus I by V, V being the volume of the system. Now, having written that, this average energy U, which is minus del del beta of log this expression, can be written as U bar is the two particle interaction minus del del beta V into I plus V, where of course I you have to do the integral yet. So so I has this integral e to the minus beta ur -1 by V. But even before that, we can break this up into, so I by V is going to be a small term because, you know, V is the volume, and here you are really looking at small contribution of interaction between two pairs. So this can be written as del del minus del del beta of ln V. And this is a function only of V. So with respect to beta is going to give 0. And then what we have is minus del del beta of ln 1 plus I by V, right? And the advantage of writing 1 plus I by V is I by V is a small quantity, so ln 1 plus x, then we can, which we can have a Taylor series expansion and keep only the first term. And then what we have, this thing is minus del del beta of I by V, right? And I is yeah, e to the minus beta ur -1. Just remember that. So in doing this, remember that we are considering only pairwise interaction between two particles. which is very valid for a gas, but in a liquid, you are going to have a situation like this, where this is interacting with this, and even this could be interacting with this and this could be interacting with other particles. But we are calculating the virial. So this item, considering such a thing, that is, you have only pairwise interactions. We're going to extend it, but it's good to keep in mind the approximations that we are doing. So next, our focus is, so U bar, after doing all of this, can be written as, because, you know, we separated out this and this became 0. Then we took a log 1 plus x equal to the Taylor expansion, keeping the first term only, can be written as two particles, the average energy between two particles can be written as minus 1 by V del I del beta, right? In that case, I mean, of course, we have to still evaluate I, but U bar, the n particle average potential energy, can be written as half n squared U bar, which means this n squared by V. So now we're just substituting this in U bar, del I del beta. So somehow if we can calculate del I del beta, then the entire n particle energy using the mean field approximation can be written as minus half n squared by V del I del beta. Now, remember, where did we come here? So we had expressed log of ZU at beta in terms of the average energy. This should be an n here, n particle energy. So this is an expression which I've just copied from the end of step 3. Please go back and have a look. And log Z of, so the ZU, U means only the contribution from the interaction term as a function of beta, could be written as n log V plus 0 to beta, the average energy of the system. And this average energy of the system, right, this n particle average energy of the system, U beta dash, we are going to, what we are going to do, where did it go? Yeah. We are going to put this here. So half, so there was a minus here, there was a minus here, it becomes plus, and half n squared by V I beta. So log ln of ZU becomes n ln V plus yeah, there was this integral 0 to beta d beta dash. This we had written in terms of di d beta, right? So thereby it becomes simplified, and we are able now to write log ZU, the function of beta, in terms of just the integral of e to the power 2 pair potential energy, e to the power minus beta, 2 particle potential energy. And since you have e to the power minus beta sitting there in front of the potential energy, 2 particles only, you have a beta of the function. So it has become much more simplified. The logs, and other than that, remember, there are these terms which are coming from the kinetic energy terms. So we are focusing only on ZU beta. Now this, after this set of simplifications, has become half n squared by V I of beta, which is just a 2 particle function. Other particles coordinations are ignored. Now our focus for some time is calculation of a much simpler quantity, just I beta, no derivative, no nothing long, etc. It has really become simple. So it's 0 to over all space that the distance between 2 particles can take, e to the power minus UR, 2 particle UR minus 1 d3R. R can take from 0 to infinity, let's assume. I mean, that's an infinite, I mean, compared to the distance between two particles, the box is infinite. That's what's going in, or else you can write 0 to L, L tending to infinity. That's also fine. So minus beta UR minus 1. Now this D3R is being written, integrated over all the theta and phi coordinates and written only in terms of, so this was D3R, 4 pi R squared dr. So we have integrated. So we have just considering a shell, right? Now the step 2 was, of course, Z 1 by n factorial h to the power 3n. This is coming from the kinetic energy term. There should be a 3n sitting here, which I have missed out. So there is a 3n sitting here, right? So there's a, so yeah, I'll just be explicit and remind you. I've added this. It is this 3n, which is missing here into ZU, and ZU has been written like this, and I beta, where there was a I beta sitting here, only 2 particle into n square and so on and so forth. And now what we do, instead of evaluating I beta at this step, we first remind you that the pressure, so from Z we can get the partition function minus kBT log Z is the free energy. And if you know the free energy, a derivative with respect to volume with a negative sign gives you pressure, right? So if you have got ln of Z, then you have to add a kBt and take a suitable derivative with respect to V, right? Well, there's a minus sign here. And the minus sign here. So what you have done is F by kBt, right? Yeah, I mean, basically ln Z is this. So we have just corrected for that and written down the expression for P. That is 1 by beta del del V of log ZU, because derivative with respect to V, these terms are going to vanish. V is sitting only inside Z of U. And what was Z of U? It was n ln V plus n square by V I beta. The consequence of which we have 1 by beta del del V n ln V plus half n square V del. So I'm just writing down the expression of ln ZU. This is the expression of ln ZU. There's a bracket which is to be closed here, right here. It's this one, bracket is there, right? And if you take the derivative, then P by kBt, this beta, you take it to the left-hand side of the equation, and that becomes P by kBt equal to n upon, if you take a derivative of ln V with respect to V, it becomes 1 by V minus half n square by V square, because 1 by V taking a derivative, we're going to get a minus sign, n square by V into I beta. So now we have an equation of state in terms of the integral of a 2-particle potential function. It's just a 2-particle potential function. It's much simpler than this. Moreover, comparing P by kBt, and this is the first term. If you didn't have these terms, then that's just the equation of an ideal gas. And corrections phenomenologically can be added by saying, okay, the PV equal to nRT, but I mean, there's a number of particles, but if you write it in terms of moles and so on and so forth, number of moles into Kb, PV equal to nRT, and these would be the correction terms, right? And these correction terms existed, I mean, from phenomenological ones. So what have we got? The expression of the correction term. And note this n square by V square is the same as this. So this B2, B3, where there was n cube, so these are interaction terms, and if you didn't know how to do the microscopics, you would say, okay, there has to be some correction terms with respect to n squared, n cubed, and these are proportionality constants, and these are fit parameters, and whatever is the experimental equation of state, you can try to fit it and get B2, B3. But here what you did is you have an expression for B2, ignoring this term. Of course, if you introduce the correlation, so we already did drastic simplifications in that we did not consider. So when calculating I beta, we are using the two particle potential. But if you said that, oh, three particles have to be interacting, you know, especially if they are liquids, I mean, you can't ignore the interaction. Then there would be more complications. You have to do other simplifications, and then you'll get terms like this. But at the moment, let's ignore. Let's see how far we can go, considering only two particle potentials. And if you consider that, if you just consider that and ignore the higher order correlations, which will give further corrections, and we can get the value of B3 in terms of whatever approximation, whatever one has to do when one keeps correlations. But so that would be in n cube term. But here, if we are just looking at two particle interactions and corrections only up to the second order in n square, the n is considered dilute. That's why you can consider, you can extend it, right? And when you consider more dense, you need more and more corrections, higher order corrections. So then this virial, the second virial coefficient, we are able to calculate from microscopics, where B2 is minus half I beta, where I beta is minus half 0 to infinity e to the power minus beta ur minus 1 4 pi r squared dr, so which is this expression. So the second virial coefficient can be written down if you know, or if you can correctly guess the u of r. On the other hand, since you know what is your virial coefficient experimentally, and assuming the mean field assumption and so on and so forth, to get the value of the right virial coefficient, you can keep guessing the right interaction energy till you get a match with your experimental value. You can think both ways. So that what you have achieved is get a microscopic expression for the second virial coefficient. If you use more better detailed analysis of the interaction, two body, three body, four body interactions, then you will have other terms, the microscopic interactions, microscopic expressions for B2, B3, B4, and so on and so forth. But even ignoring that, with the assumptions that you have a microscopic expression for the second virial coefficient, which is written in, for simplicity, only in terms of two body interactions with the beta setting. Of course, if the interaction is higher, the interaction energy is higher, it is penalized. This comes with a minus sign. And so you have that. And what to do with that? So just to remind you that the second virial coefficient, of course, is a function of kBt, and you can explicitly see that there's a beta sitting here. The integration is over r. So even after integrating, we'll have a beta in the expression for B2. And this is what we have already discussed. The point is, how do the correction terms affect the validity of the ideal gas equation? When do the ideal gas equation needs correction? And the factors which are affecting the validity of the ideal gas section is n by v. If n by v is more, and you have to consider interaction terms, and the first thing you consider the second virial coefficient. And the second virial coefficient can be written. I think this pi square is wrong. Where did this pi come from? Yeah, there was this half and there was this 4 pi. So you will get 2 pi r squared dr. So the B2 can be written, right? In terms of minus half I beta, and this I beta, yeah. So B2 is this minus half. As a consequence, you get B2 equal to minus 2 pi 0 to infinity e to the minus beta u r minus 1 r squared dr. Now, further discussions I shall continue in the next class. I need some corrections here. Okay, so let me see how to stop this. First of all, stop share.